Hello, my name is Gilles Demar and I'm presenting a joint work with some colleagues of my laboratory located in the north of France. In this work, we propose a new notion of explanation for classifiers based on boosted tree. First of all, I want to recall that classification is a major task in machine learning. Different predictors have been proposed in the literature. One can cite classifiers based on trees such as decision tree, random forest, and boosted tree, or other type of classifiers such as Bayesian network or neural network. The problem is that efficient predictors are often black boxes, but it is important to provide explanations on decisions made by such classifiers. For example, it is required in Europe since 2018. This problem stimulates much research in AI for the past couple of years, and this part of AI is called explainable AI. In order to compute explanation, you can use agnostic approaches. They suppose that the classifier is a complete black box system. There is no knowledge about it. One can cite, for example, Lime, SHAP, or Anchor. Such approaches are useful if the classifier is a CNN, for example, but they can provide incorrect explanations. That is, the same explanation can explain different classes. So, they cannot be used with critical systems. Our approach is a model-specific approach. We consider classifiers based on trees, such as decision trees, random forest, and boosted trees. Thus, we associate to the predictor a circuit that have the same input-output behavior, and we consider this circuit for the verification task. Using this approach, we can provide formal explanations that have theoretical guarantees. The resulting problem is that the scalability can be an issue. In this work, we deal with boosted trees, which are known to be very efficient when dealing with tabular data. In this presentation, I focus on binary classification, but our results can be generalized to the non-binary case. In this example, we have a boosted tree with 4 attributes. 2 are numerical, 1 categorical, and the last one is a Boolean. Consider the following instance. For the first tree, A4 is 1, so we follow the right branch. A2 is greater than 1, so we also follow the right branch. We can continue to follow the last branch for the last 2 nodes, and the weight for the first tree is 0.3. The weight for the second tree is 0.5, and the weight for the last tree is 0.1. Then, the weight of the sum of the weight of the boosted tree R is greater than 0, and X is classified as a positive instance. A sufficient reason is a form of abductive explanation. It answers the question why the instance has been classified like that. A sufficient reason is a subset of the instance, such that any extension of it is classified in the same way. A sufficient reason is subset minimal. It does not contain irrelevant characteristics. Consider the same instance as the previous slide. A sufficient reason for this instance is A1 is 4 and A4 is 1. This table summarizes all possible extensions of this sufficient reason. You can have A2 greater to 1 or not, and A3 equal to B or not. For all these possible extensions, the sum of the weight of all trees is always greater than 0, and then is classified positively as X. There exist different works to compute sufficient reason for boosted tree. The first one uses a satisfiability modulo theory approach. The second one, a max-set encoding. The problem is that the scalability of both approaches is an issue. To overcome this problem, we propose the notion of tree-specific explanation. Such explanations are abductive and can be used as a preprocessing step. The interest is that the computation of tree-specific explanation is done in polynomial time. A tree-specific explanation is a form of abductive explanation. Here, all trees are considered independently. When considering an instance, one looks for all least possible weight reachable by each tree. Consider the same instance. A2 equal to 3 and A4 equal to 1 is a tree-specific explanation. For each tree, we highlight in blue the reachable leaves and keep the smallest one. For example, for the first tree, it is equal to minus 0.3. For the second one is 0.5, and for the last one is 0.1. So the sum of the least weight for all trees is greater than 0 as the instance x. On the contrary, if we take the subset A1 is equal to 4 and A4 is equal to 1, it is not a tree-specific explanation. Here, for each tree, we highlight in red the reachable leaves and keep the smallest one again. For the first tree, it is equal to minus 0.3. For the second one, it is equal to 0.3. And for the last one, it is equal to minus 0.4. Here, the sum of all least weight is less than 0, whereas x is classified positively. For computing tree-specific explanation, we can use the greedy algorithm. One removes one feature after the other. We compute the sum of least weight. If it is positive, we can definitively remove this feature. Otherwise, it is skipped. Of course, order matters. Different orders produce different tree-specific explanations. Since this algorithm runs in polynomial time, one can apply this several times using different orders and return the smallest tree-specific explanation. In general, tree-specific and sufficient reason do not coincide. Indeed, in tree-specific, the trees are considered independently, but some least weights can be incompatible. It is, for example, the case for minus 0.3 for the first tree, where we are on the branch where A3 is not equal to B, and not 0.4 for the last tree, where we are on the branch where A3 is equal to B. So the tree-specific explanation may contain irrelevant features, but for a tree-specific explanation, we can extract sufficient reason. Thus, tree-specific explanation can be used as a pre-processing step for X reason. I present now an empirical evaluation of this pre-processing. We consider 50 datasets with different number of classes, different number of features, and different number of instances. We use XGBoost to train the model with default hyperparameters. We use a tenfold validation. We select each time 50 instances from the test set, leading to a total of 4,000 instances. And we compare X reason with or without the tree-specific preprocessing step. For each instance, we limit the time to 100 seconds. First of all, let us compare the computation time. In this graph, each dot represents an instance. The x-coordinate is the time needed by X reason with the preprocessing to solve an instance. The y-coordinate is the time needed by X reason alone to solve the instance. So dots above the diagonal correspond to instances where X reason alone is slower to solve an instance. It is clear that using the preprocessing step improves computation times. We can also remark here that the number of timeouts is substantially reduced using this preprocessing step. Now if we take a look to the size of the explanation, we have this graph. Here dots represent the reduction rate. So dots above the diagonal shows instances where X reason is the reason of instances is smaller than the reason with the tree-specific preprocessing step. Here again, it is quite clear that in a large majority of cases, the size of explanation is reduced. And of course, one prefers smaller explanations that are easier to understand. Let me conclude. We introduce in this work the notion of tree-specific explanation. Such abductive explanation can be computed in polynomial time and can contain redundant characteristics. Using them as a preprocessing step to compute sufficient results is valuable. The computation time and the size of explanations are both reduced. You can use our library PixSci in order to compute tree-specific explanation. In a short-term perspective, we plan to exploit user preferences and to compute contrastive explanation for boosted tree. Thank you.